everyone. My name is Derya. I'm an assistant professor in electrical engineering. And my research focuses mainly on the confluence of communications, computation, and coding in networks. I am more on the theoretical side, but I will try to summarize my motivations and several key problems that I have worked on so far and my current research directions. So the main motivation of my research is, why do we need to compress massive amount of data? Like most of the main reason for that is we have limited resources. When we consider from a networking perspective, in general, we have to work with finite bandwidth. And in addition to that, like we have privacy issues, we have like sensitive data that we do not want to disclose. That's why we have to compress the data accordingly. And in addition, we might have lots of redundancy because we have like geographically located sources that might contain correlated data that is redundant to transmit at the same time. And in addition, due to the real networks that we work on, we might have topological constraints that eliminate some of the possibilities, and we have to compress the data in order to optimize the performance of the networks. So the broad goal is to develop distributed computation or storage techniques for next generation wireless networks. In order to motivate why we need to compress or communicate massive amount of data, this has lots of applications in different domains, including classification or federated learning and machine learning applications, or from an information theoretical perspective, like the caching problem or the side information problem, or successive refinement techniques that use like a compression of massive amount of data. Or from a signal processing perspective, the main quantization models or hypothesis testing results, like distributed implementations are already existing, and they can be improved using more fundamental results from communication theory. So my goal is also to make use of the underlying redundancy in data and also the tasks that we want to compute in networks in order to recover a sparse representation that we are interested in. Okay, so one of the directions of my research is to fit models to communication networks. I basically use Poisson tessellation models or other kind of tessellation models to be able to mathematically model these networks. And these models turn out to be very accurate in analyzing this kind of communication networks where nodes are randomly distributed and when we have large amount of nodes in the network. So one direction is access networks. So when we have large amount of nodes in the network, it's possible to understand the trade-offs between the communication rate that we can achieve versus the energy expenditure that we need to do. So obviously there is a trade-off between these two. And depending on the type of communication protocols that we want to use, it's possible to understand the relation. So I put some example figure here, like that explains how the rate changes with respect to the energy requirements of the system. But of course, like if you are interested in anything that I have talked in this presentation, feel free to send me an email. So I will not go into the details of this. So another problem is, like a very popular problem in nowadays is IoT. Like when we have like huge number of users that want to simultaneously access a point or access a base station. So it is very critical to schedule them effectively in order to prevent congestion problems. So, this becomes very critical, especially when we deal with delay-sensitive communications where each device has to send the payload within a short time. So we developed some sliding window protocol to be able to satisfy the delay requirements and delay requirements of the users. So another direction of my research is trading off the delay and throughput requirements for different applications. Some applications like file download requires very high throughput, but the delay, the per packet delay for those applications might not be very relevant. But some applications like streaming might require very low delays. So depending on the delay that we can tolerate and the throughput that we want to provide, we can understand what are the fundamental limits that we can achieve. And accordingly, we can find the best operating regime for the application that we want to run. So this was a project that I was working during my postdoctoral research last year, which was sponsored by Intel and also DARPA. And right now, I am also the subcontractor for the DARPA project. Okay, another direction is device-to-device communications. Again, in a very huge cellular network scenario, like what are the limitations of caching, storage, when devices can only communicate with proximal users within their neighborhood? So I studied the theoretical limits for this problem using some actual data set that we have obtained from Netflix. So the main reason that we study video is basically it consumes most of the wireless bandwidth. And we know that like by deploying small cells or local storage, we can significantly reduce the bandwidth that we require from the base stations. And okay, I'll skip this, but one of my main motivations is the geographic variation of the demand, which happens in real life. Like the real demand varies geographically. And accordingly, like we have to optimize the deployments of the base station according to the variation of the demand. That's another direction that I'm interested in. And basically, like using all the demand profile and the network structure, we are interested in understanding the limits of geographic caching. So where to place the caches and what files to place in order to minimize the delivery delay of the content or the bandwidth usage in the network, which is very critical. Okay, like for that, like I developed some models that are based on proximal communications, or like device-to-device or peer-to-peer communications, where these models are based on exclusion-based models, where files with high popularity should be cached more often than files with low popularity. And depending on the popularity, like I define an exclusion range as a proxy for optimizing the caching distribution. Okay, I'll not go into the details of this, but this kind of models especially suit for heterogeneous networks where nodes have different power requirements or nodes have different storage capabilities. And this brings lots of randomness into the network that we consider. So what I have shown is basically in order to achieve some desired performance using caching, so what should be the minimum cache size that we need to be able to attain that performance? So what we have shown is basically compared to random approaches that is shown with this green curve, which requires higher cache size. It is possible to significantly reduce this cache size using exclusion-based models. And these models can be even refined by using some soft potential-based models that are inspired by some random connection model in wireless networking. So here, like you can see one dotted curve and one dash curve. Basically, the closer they are to each other, the better the performance is, because it prevents the overshooting, and we do not want to overrun the cache capacity. So this kind of models help us understand what are the fundamental limits of storage and how, in terms of cache probability.
Yeah, are you wrapping up now?
Okay, I'll wrap up quickly. And the directions that I'm interested in, like to further compress data to understand the limits of functional compression. What is the minimum amount of data that we need to transmit in order to attain some task? And for that, like we developed some architecture for workload distribution in large-scale networks. I'll not go to the details of this. And I'm also interested in directions that involve machine learning for translation from a language to another language. So I won't be able to discuss the details of this. Just to summarize, like these are some courses that I started to teach this year: digital signal processing and digital communications. And since I'm running out of time, like please send me like your questions with email, or we can discuss at the end of the presentation. Thank you.
Thank you, Derya.